Hello and welcome, ladies and gentlemen, to the last webinar of the series about the new GOM software version V8 SR1. My name is Jens Scharfenstein and I have Chris Simmons next to me for the question and answer section. So if you have any questions, use the Q&A section and Chris will answer them immediately. This webinar will be recorded so you can view the content again or share it with other people in your organization. We will show you how and where you can watch this video again, and also where you will find additional information at the end of the webinar. The topic for today is airfoil inspection. First we will introduce the new computation method for camber lines. Then we are going to show you improvements on edge circles, we will talk about the maximum profile thickness, and we will show you the profile twist function and in combination on the linked actual stacking point. So let's start with the camber line. In V8 SR1, the functionalities related to the camber line have been improved and extended by a new type of calculation. Therefore, the question arises, how is the camber line defined? The camber line describes the camber of an airfoil profile. It is defined as the curve which is halfway between the pressure and suction sides of the airfoil profile. There are different ways to construct a camber line to meet this definition of being halfway between the pressure and suction sides. For this reason, in V8 SR1, in addition to the existing profile mean line construction type, the skeleton line is introduced. The geometry of the profile mean line and skeleton line are different. The difference relates to the way that each construction type achieves a curve which lies halfway between the pressure and suction sides of the airfoil. Let's first review the profile mean line. The profile mean line is constructed through the center points of a series of maximum inscribed circles. Using this type of construction produces a camber line which lies halfway between the pressure and suction side of the airfoil when measured normal to the profile. This displayed circle is representative for all the other inscribed circles. Alternatively, the skeleton line can be used as another type of camber line in V8 SR1. Its construction produces a camber line which lies halfway between the pressure and suction sides of the airfoil when measured normal to the camber line. Due to that different construction types, the geometry of the profile mean line and skeleton line are different. The company design standards or specifications for the airfoil you wish to inspect should be used to determine which camber line type to use. Okay, so let's have a live demo inside the software. I open this and we have prepared a project over here. And before starting with this, I will explain a bit the content of this project. So we do have two sections and they are placed in the same height so that they are equal in its shape. Additionally, we do have stacking points. The stacking point is the intersection point of the section's plane and the world z-axis. So let's have a look to the section. Here's the stacking point. And now I would like to select section 1 and open iInspect, go to the airfoil icon to access the camber line dialog box. Alternatively to this way, you could also go via the menu bar and inspection to analyze airfoil and open camber line over here. But I want to use the iInspect and open the dialog box. So to decide which type you want to choose, you open the expert parameters and here you can choose between the profile mean line and the skeleton line. For section 1 I would like to create the profile mean line. Hit OK. Select the camber line. Press Tab to change the color that you are able to decide the differences, and the skeleton mean line I will change to a pink. For section 2, I create via InSpect the Camber line of type skeleton line. OK this, select this and change the color to green. Now I will zoom in a bit that you see the differences of these two construction types. Over here you see a gap. Yeah, and due to these differences in the shape, please refer to the specifications or standards inside your company. Let's go back to the PowerPoint. After the Camber line, I would go ahead with the profile edge circles. V8 SR1 provides additional functionalities for fitting profile edge circles. Two new types have been added. In addition to the existing fitting tolerance option, automatic fitting can now be used. Also, it is now possible to constrain the center point of the fitted circle to the Camber line. I will demonstrate the new functionalities with an example. Let's review a typical airfoil section. A Camber line has been created and the leading edge circle has been fitted using the workflow of older software versions with a fitting tolerance of 0.1 mm. And here, highlighted in red, we see the points of the section which are initially considered by the fitting process when creating the leading edge circle. This point selection includes outliers. Next I will show the effect of halving the fitting tolerance to 50 microns. Using a lower value for the fitting tolerance results in a fewer points being initially considered by the fitting process when creating the leading edge circle. The size of the fitted circle is also affected by the lower tolerance. In this case, the edge circle is smaller than the one created with a larger fitting tolerance. Sometimes the inspection specification requires that the center point of the fitted edge circle is constrained to the Camber line. This can now be achieved in V8 SR1 by enabling the constraint center point on Camber line. By enabling this constraint, the edge circle is centered on the Camber line. The initial selection of points considered by the fitting process when creating the circle is not affected when this constraint is enabled. But the algorithm may sort out some of the points to ensure the requirements. In this example, with the edge circle constrained to the Camber line, the leading edge circle became smaller compared to the previous parameter settings. In V8 SR1, it is possible to enable automatic fitting as recommended setting compared to the manually chosen fitting tolerance. Using the default automatic fitting, the software detects the points in the high curved part of the edge, as you can see marked in red. These points are considered by the fitting process to create the edge circle. The user-defined fitting tolerance will not be applied in this case. A needle plot of the section curvature illustrates the behavior of automatic fitting. Only the high curve areas are considered. An important benefit of using automatic fitting by default is that fitting parameters and point selections are shape-driven using the low curve information from the section. So, in a live demo I will show this in detail for section 1 and the skeleton line and the profile mean line. So we select section 1, open the dialog box for the edge circles over here, set the value to 0.1 to get the initial circle, and click OK. So now the leading edge and trailing edge circle are created, and I would like to focus on the leading edge circle. I select the circle, and it's selected over here, and by right click I access the edit creation parameters. Okay. Over here you see the point selection including the outliers, so these points are used for the fitting process. And now I would like to halve the fitting tolerance to 50 microns and have a look for the selection. It decreases. And also these points include the outliers. So now have a look for the center point. This is not on the camber line, but we would like to have it on the camber line. Therefore, we apply this constraint, and the center point is directly linked to the camber line. The selection of points stays the same, but we have more outliers. So the fitting algorithm changed a bit, and the circle got a bit smaller. In the past, the fitting tolerance was not the easiest value to choose, so it was often a decision which is the right one, which not. And therefore we introduced the automatic fitting. So it's an individual shape-driven fitting process for your edge circles. And therefore I apply this, and we have a very nice selection of the points, and the circle fits very nice to the leading edge. And this is the reason why we recommend this functionality. With OK, I create this automatic by automatic fitting created circle. OK this. So now let's have a look for the maximum profile thickness. In V8 SR1, the functionalities related to the maximum profile thickness have been improved and extended by a new type of calculation. In addition to the pre-existing distance type in V8 SR1, we introduced the new circle type. The maximum profile thickness type circle is directly derived from the construction of the camber line. It is the maximum inscribed circle with the largest radius. The maximum profile thickness type distance is constructed from the tangent contact points of the maximum profile thickness circle. On this slide, you see both types applied to a gently cambered airfoil. In this example, for a nominal section, the difference between the diameter of the maximum profile thickness circle and maximum profile thickness distance is small and measured at a submicron level. The type maximum profile thickness distance is important for measuring the maximum profile thickness of highly cambered airfoils. I will explain this more in detail on the next slide. Here's an example for a highly cambered airfoil. As can be seen, for such an airfoil profile, the circle type of maximum profile thickness can underestimate this dimension. This is due to the large separation between the two tangent points on the suction side of the airfoil profile, which leads to a gap between the maximum inscribed circle and the airfoil profile. To overcome this, the distance type of maximum profile thickness can be applied. The distance type of maximum profile thickness is constructed using the three tangent contact points of the maximum inscribed circle. First, a midpoint is created between the two contact points of the maximum inscribed circle on the suction side. Then a line is constructed between this midpoint and the remaining single contact point on the pressure side of the airfoil profile. This line is extended until it intersects the airfoil profile on the suction side. The maximum profile thickness distance is the distance between the intersection point of the suction side and the single maximum inscribed circle contact point on the pressure side of the airfoil profile. The company design standards or specifications for the airfoil you wish to inspect should be used to determine which maximum profile thickness type to use. So, for this example, I will show you in another project on a highly cambered airfoil the differences. So here we have the airfoil. I hide this and let's zoom into the section. So we have again two sections. For section 1, I would like to create the maximum profile thickness of type circle. So select circle and click OK. Over here we have this gap we want to overcome. and therefore I use for section 2 again maximum profile thickness, but this time type of distance. Click OK, and it's quite obvious that the distance type overcomes this gap. So after this, I would like to talk about the profile twist and the linked actual stacking point. The profile twist function is used to inspect the form and position of an airfoil section. In V8 SR1, this function has been improved and extended. The Gaussian best fit has been improved. It now produces a shape-driven alignment which is insensitive to the higher point density areas of the section. The Gaussian best fit constraints options have been extended too. It is now possible to define transformation constraints for the Gaussian best fit alignment in a local coordinate system. The checks for reporting form and position errors have been improved. More deviation labels for describing the statistics of the profile deviations are now available. The maximum and minimum deviation labels are now toleranced. Finally, there are also some small improvements to the dialog box to remove a redundant item and rename an input field label. Please review the direct help for a full description of profile twist. In addition to the enhancements for the profile twist, we introduce in V8 SR1 the linked actual stacking point. The new measuring principle combines the nominal stacking point and the inverse profile twist transformation. This combination is required for longitudinal inspections between sections. The alignment of the actual section to the nominal section is central to the profile twist function. This is performed using either a Gaussian or Chebyshev best fit. The resultant alignment transformation is used to determine the positional error of the actual section with respect to the nominal section. Following the alignment, the actual airfoil profile is compared to the nominal airfoil profile to determine the form errors. During the alignment, all 3 degrees of freedom are calculated simultaneously. These are the rotation about the normal of the section plane and the true translation in the plane. To ensure this is clear, I will show the 3 components of the alignment separately. The origin of the reference coordinate system for the alignment is created at the intersection of the world z-axis and the plane of the section. Here you see the result of rotating the section about the origin of the reference coordinate system. The orientation of the reference coordinate system for the alignment is created by projecting the world x and y axis onto the plane of the section. Here you see the translation of the actual section in x direction of the reference coordinate system. And finally, here you see the translation of the actual section in the negative y direction of the reference coordinate system. I will show the checks used for inspecting the positional error during the software demonstration. For the majority of airfoil inspection applications, the 3 degrees of freedom transformation previously described is applied without further constraints. However, for some applications, it is desirable to apply constraints to the alignment to prevent or limit the rotation and translation. It is common for the section positional tolerances to be used as the limits of the rotation and translation. In V8 SR1, the profile twist constraints have been extended. It is now possible to apply these alignment constraints in a local coordinate system. For our upcoming investigations, we keep the global coordinate system. Following the alignment, the actual airfoil section is compared to the nominal airfoil sections to determine the form errors. I will show the form error checks during the following software demonstration. As mentioned before, in V8 SR1 we introduced the linked actual stacking point, which is often used to often used for longitudinal inspection between sections. This new measuring principle creates the theoretical actual stacking point using the nominal stacking point and the inverse profile twist transformation. So let's start the demo. Therefore, I select section 1, make it exclusive by hitting E, and then via IInspect we can select the dialog box for profile twist. I open the constraints and we have our profile over here. I highlight the global coordinate system. Yeah, so Z is facing towards us, X to the right, and the Y-axis is facing to the top. So then I also highlight the stacking point 1. It's coincident with the Z-axis, and I want to use the stacking point 1 as inspection point. By doing this, you see, I zoom in a bit here, slightly to see, this is the reference coordinate system. This one. So I turn off the global coordinate system, you see it over here. And for our inspection, we could use a local coordinate system, but I would like to stick with the global coordinate system. And at the end, we could enable some constraints or limitations for the transformation or the best fit. But I keep it as it is and say, okay. So, selecting the twist. On this point, I would like to check the form errors. Therefore, I have selected the twist, hit the tab key, and now I can edit a tolerance. Actually, there's no tolerance, but now I set it manually to 0.5 millimeters. So now you see here a tolerance band, but I want to make sure that you understand it in the right way. This is scaled. The scaling factor of 1 would display this, the real size, but to make it more obvious, we scale it to 10. I close this again. So now we have added the tolerance band to this. And we need now to check the form and the position of this. So open via IInspect the checks. The twist is still selected, and now we can check for the position X and Y, also the rotation about Z. And let's say we take the minimum deviation label for the twist form and the maximum deviation label. You could also choose the arithmetic mean, sigma, or the range for the form check. But I think this is good enough. So, like this. Inside the table, we have a summary of our results. And we see immediately that the minimum and maximum deviation label got the tolerance from our profile twist by plus minus 0.5 millimeters. And I would like to add a tolerance to the positions. So I select, for example, the X and Y, hit the tab key, go to tolerance, set it manually to 0.1 millimeters, for example. And for the rotation, I select the rotation about Z, manually set a tolerance 0.25 degrees. Close this, and the entire inspection is updated. So that's about the profile twist. And now I want to explain a bit more the linked actual stacking point. For now, we only have the nominal actual stacking point. To create the linked actual stacking point, I go to inspection in the menu bar, analyze Airfoil and select over here the measuring principle linked actual stacking point. Open this, and as you see the dialog box, you have to choose a nominal stacking point and a profile twist. Stacking point is stacking point 1, profile twist is this one, and I OK this. So let's open this one and make the linked actual stacking point visible. Then I select both, open iInspect, and change the visualization to geometry, that we do get the coordinates of these 2 points. Okay. Over here we have our nominal stacking point. X and Y is 0 and Z is 600. This is due to the position and height. For the twist, we had this transformation, and the linked actual stacking point is to have the inverse values. So X is plus 0.03 and the twist X is minus 0.03. And for Y it's the same in the opposite. So now we have created the linked actual stacking point to calculate, for example, the bow if we have more sections. Okay. So I'm going back to the PowerPoint. Yeah, we have almost reached the end of the webinar. There are also additional informations we would like to mention. You can download a beta version of the V8 SR1 already. GOM has launched the open beta program in order to give you the opportunity to try out new functions and enhancements without affecting your daily business. The V8 SR1 will run with the current V8 license, so there's no need to update your license if you are on V8. Please find more information and the software packages under the following path: support.gom.com, then download software, overview, GOM software V8 SR1. The final release is planned in mid-January in 2016. As mentioned at the beginning, this webinar was recorded. You will find the video for download in the support area and also on the GOM Metrology YouTube channel. In addition, we have produced video tutorials for the new functions, which are also available on YouTube and in the GOM service area for download. You can find a detailed list of new features in the direct help. We also implemented the links to the video tutorials for the new functions. This was the webinar Airfoil inspection. We will stay online for a while to answer your questions in the Q&A sections. Thank you very much for your attention. We hope you enjoyed it. Have a nice day and auf Wiedersehen.